Thank you. This is a joint interdisciplinary work between our group, this is Franz, Alisa, and Interactive Media Lab Dresden. This is Dachselt, and Méndez is actually here today. And yeah, by now we are all familiar with what. And the description of it before. Often. Well, just to recap simply, but what we can say is that we can express knowledge about atomic concepts, things like delivery drones, for example, or charging stations. And we have access to complex concepts as well. We can express within, for example, a component that is located on a certain part of landing gear, for example. And we can combine these complex these concepts together to form a sentence. For example, we can talk about everything that has there is a large battery drone is actually a drone that has a part which is a large battery, and the other part from the type of the concrete part refers to concrete domains, which we've also heard about. And in this work, we focus only on two specific concrete domains. The first one is called this is the domain that also Franz contributes. So what we can express here is that we have three types of constraints. The first one, we can state specific values for certain variables. So we can say, okay, we have battery percentage with 75%. You can also state constraints of the form battery percentage is greater than 30%. And we can also relate two different variables, two different percentages together and talk about the difference between them. For example, the battery percentage one is the difference between it and battery percentage two is 20%. The other concrete domain is the DQ, where we can use linear equations to express these things. And in this particular case, we have an example where we can say, we can talk about the battery capacity in terms of discharge rate. So we can say the battery capacity of 30 ampere hour is actually equal to 4 hours normal discharge rate plus high discharge. And another example is a battery with 30 ampere hours is the equivalent to 8 normal discharge rates. Sorry, 8 hours of normal discharge rate. And yeah, lastly, now we will have the complete logics that we can talk about. And these are basically the L bottom with the DQ diff concrete domain and the other version with the linear equations. So in the case of the L bottom with DQ diff, we can express concepts like the things that have a battery and that battery percentage is greater than 25%, for example. And in other logic, we can express axiom statements where we can say, okay, every drone such that the 2 hours of high discharge rate is equal to 30, such a concept is also a large battery drone. So now we can express these sentences in our logic. And what we want to do is to basically explain reasoning results in these projects. And this is where Evonne part comes. So Evonne is basically a web application that we originally designed to explain description logic entailments. And what Evonne does is generating proofs as explanations to those entailments. And these proofs are like equipped with additional functionalities that allow user to explore them. So for example, you can cut parts of it, hide or show certain parts, You can even look at the proof in a different layout depending on the domain you're considering, and focus on certain parts of it with additional more explanation to show certain features of the proof and many other things. And what we do in this work, we take it on and we extend it with explanations for concrete domain reasoning. So let's assume now we have an ontology that describes the domain of delivery drones. And let's say that in our ontology, we know that our delivery drone satisfies the constraints of 8 hours of normal discharge rates, is equal to 30 ampere hours. And we also have another axiom that tells us, okay, this delivery drone is one satisfying the other condition that 1 hour of high discharge rate plus 4 hours of discharge rate is equal to 30. And we also know that anything that satisfies this constraints, 2 hours of high discharge rate equal to 30 is a large battery drone. From these 3 statements, actually, it follows that the delivery drone is a large battery drone. And what Evonne provides as an explanation for this interior is simply a proof. It's maybe nothing that we already do to stay up. This is the big conclusion. But we call this proof a combined proof, actually. In our example, it consists of 2 parts. The one part of the proof talks about the numbers only. And this simply explains in a stepwise how the constraints that we have in our toolbox, in our ontology, are being used to infer new constraints, eventually be used with the other part of my ontology. So the gray boxes represent basically inference tools, and the way these numbers are used are coefficients. So basically, 1 is half if I multiply it by this equation, and then into this one, I think that 8 are equal to 15. And simply, if I then multiply it by 2, I can infer this new constraints, which happens to be part of my knowledge, which is this axiom already there. And I can now combine them in the second part of our combined proof, where we just apply standard Julián reasoning, and it's simply like plausibility. And A by B implies C, and B by C. So we now can move away from the number reasoning and go back to this material. And we have an explanation that will tell us how the finite conclusion has been derived. Now, the issue here is that you can see easily how this thing can get more complex. Like by simply having harder or less friendly coefficients, then multiplication might become a bit more difficult. Also, the size of the proof. So what we want to have is some alternative way of providing such explanations that will move away from doing this multiplications. So the way I like to think about this is that proof approach this in a way that they take this knowledge, they take these constraints, and try to use them together to come up with a new kind of constraint that eventually I can use later. But we can also look at this in a different way, where we can concentrate about the solutions of these constraints instead. And this is the idea for these alternative explanations, is that, okay, before I tell you what the alternative explanation is, I'll just tell you about how it is presented in Evonne. This part, it's exactly the same example again, where we show the original system and the conclusion that follows from it. To the right of it, we see an instantiation that is a solution of the system. I mean, in our example, we have only one solution, so it's a bit simple. And in this part, the user gets to choose which variables from our system they can assign which axis of the plot. And the explanation is the plot itself. And the idea is since I'm trying to show that this system implies this equation, this means that whenever the system has a solution, then this solution is also a solution for the implied equation. So, and since we're looking at equations with two variables, so in the 2D space, this would be simply a point. The solution would be a point. So the intersection of the green lines, which is the system, the original system, must also be a solution for the purple line. Hence, they all should intersect at the same point. And this is how we can show that the green lines imply the purple line. Now, this is in the case where we have only two variables. When we have more than that, and we still want to be able to use this, so we use bucket dimensionality reduction, and we use the solution space to achieve this. And what I mean by that is that, so in this a new example, what we can show is that whatever value the user chooses for the free variable, and as you can see, always, whichever plot axis, so whichever space it is defined, we will always see that these green lines intersect in one point, and that point exactly the same where the purple line also intersects. So no matter the value that is chosen for the free variables, this will be reflected in the solution, and this will be also shown in the intersection of the lines. This is the case where we're trying to explain a positive intent. What about the negative one? So when you have like inconsistencies, and we can also use this. So in the case where we have no solutions, whatever the user tries to, whichever value the user tries to assign to the variables, there will never be a state of the plot where all lines intersect, because there is no solution. But this is only true if we define a space that covers all the equations, because it is possible, for example, that if we change to x3 and x2, the third equation does not talk about these variables. So technically, it's not plotted, and we only see three lines, and it's possible to actually have an intersection of these three. Now, this does not contradict what I said previously. It's simply incomplete. This space does not show me all equations. And to account for this, we show the contradiction in a different way. So once we fix these values, even though that we managed to get an intersection, there's clearly a contradiction that has been raised. And when I try to fix this contradiction by assigning different values, the contradiction is not there anymore, but simply I also lost the intersection. So the interaction between these two multiple ways of going, trying to assign like correct values and then find an intersection will help the user understand why there is a contradiction in the first place. At least that's the idea. Moving to the next domain. Now let's go back to our ontology, where we have knowledge about draws. And let's assume that we have the following constraints about the battery percentage. And these battery percentage have been taken at multiple checkpoints. So the difference between the battery percentage at the beginning versus at checkpoint 1 is 25%, and between checkpoint 1 and checkpoint 2 is 20%. And we require that after checkpoint 2, the battery percentage should be greater than 25%. And we know that at the beginning, our drone, the battery percentage is 65%. Then with this knowledge, our drone would not be permitted to fly because we have an inconsistent set of constraints. And to explain this, we do the same thing again. We can provide the proof. But unlike the linear case, we do not just use that coefficients in fact to infer new form of equations, but rather we use a set of saturation rules that allow us to get all relevant constraints and use these directly to build our proof. And the advantage here is that simply every such rule correspond to an inference directly in the proof. So basically, this proof explains why we have an inconsistency, because we can derive a value for the second, the battery percentage of Z12 that is less than the minimum required by this consent. And again, we can easily see how this proofs can grow also large. And in the same way, we want an alternative way of explaining this that can leverage the nature of the complete domain. And wrapping here, our job is a bit easier than the linear case, because constraints of this form, this difference constraints, can actually be represented as graphs. And this is already well known. So x minus y less or equal to b, it can be seen as a graph where y and x are unknowns, and there is an edge between them with the weight. Our domain, the VQDIF, does not exactly have this type of constraints. So what we have is equality of this one, x minus y equal to b. This is simply just two edges. So this is just two constraints of this form. So this is easy to do, but the other constraint that we have, where we have strict comparison, first we need to make this binary to create an edge. This is relatively simple. We just have a new symbol or new variable that we make sure that we always evaluate with 0. And we get our binary comparison. And to be able to go from strict to less or equal, we just subtract a positive value that is very small. We don't care what this value is, as long as it's very small positive value. And in this way, we will get our edge. And it will go from 0 to x with b minus epsilon. Now, why am I talking about this? Because now we can explain unsatisfiability of difference constraints using the idea of negative cycles. And this is how we present this in Evonne. The idea is that if we have a system of a set of difference constraints that is unsatisfiable, then this means the corresponding graph must have a negative side element. And on the left side, we present the system as it is. This is exactly the same example we saw before, but with the necessary transformation to make less or equal instead of strictly less. We see the value of the cycles in our graph that makes the constraints set unsatisfiable. And this is the exact graph in which the cycle exists. And what the user can see by clicking on any of the equations, it will trigger an animation in the cycle that shows how this. Oops. Yes. So yeah, by clicking on any of the equations, we can see the animation for the cycle. And the user can also see not just why this negative number is a problem. They can also click on any of the variables and assign a specific value to it, which then will allow them to propagate that value along the cycle to create a contradiction. So basically, because of the negative weight, assigning 1 to or 100% into battery percentage 2 will then lead to something that says 1 is less or equal to something that is strictly less than 1. So this is basically the contradiction. That's why our system is unsatisfied. We can also use negative cycles to not just explain negative reasoning results, but also to explain newly inferred constraints. But this will require us then to take the conclusion that we try to prove that it follows from the system, negate it, which will give us two new constraints, and then show that each of the corresponding cycles has a negative cycle. Each of the corresponding lab has two negative cycles in it. Now, this might get some used to, because it's when we need to take the positive thing that follows negated and then see that we have the inconsistencies in both cases. And this dotted edge simply we use to try to encode two cycles in one graph. So it's either this or that, but both of them will have a negative weight. Okay. These are the ideas for alternative explanations for these type of entailments. We have implemented this in Evonne. We did some evaluation for our implementation. The performance benchmark, we did over 100 proofs. There are no real ontologies out there that use complete domains. So these proofs we had from a previous paper where we used to evaluate our reasoner. And just being able to render all these visual explanations, it happens relatively fast. And we also did another form of evaluation where the user study, where we asked people to compare between proofs as explanations versus the alternative visual explanations. We had 11 participants from our colleagues and students. And the results that were not on the same level for both domains, let's say. Everyone agrees that the visual explanations add to the understanding of the numerical reasoning and how it is happening. For the case of plots, people found it hard to trust them when we talk about more than two variables. It was not so easy to believe when they had to change between different spaces and keep track of all possible values. So they were like trust issues with it. However, cycles on the other hand were preferred. It was like much easier to follow. They didn't have to do any math to just try to take two constraints together, try to apply one rule to get where this comes from and how do I use it later. It just, once I believe in the idea of whenever the weight is negative, something is unsatisfying, then by just seeing it, it's an enough explanation. So it was mixed. So simply to summarize what I said, basically we extended Evonne with these types of explanations that allow us to handle logics with two specific concrete domains in the form of proofs, and to provide alternative visual explanations. Those are the negative cycles as well as the equation plots. And we have provided an evaluation for our implementation. This basically on two levels. One is more about the ideas themselves in the form of qualitative user study, and the other about the implementation itself and how well it behaves. As for future work, we're working on addressing some of the issues that the user study participants have raised. The other direction that we want to tackle, let's say, is providing explanations, but for the negative reasoning result. So basically when something does not follow. And we already have something like this in Evonne. However, it doesn't handle the case with numbers. And this is what we like to do next. Thank you. That's everything.
Thank you.